So let's talk about how the calculations are done working with floating point numbers. And we will focus on addition, subtraction, multiplication, division. All other operations like the sign of something or is implemented in a computer by a sequence of plus, minus, times or divided, believe it or not. So what is done if we want to add or if we want to subtract? Here in my script, I've written all that stuff and the examples I will do on my paper. Let's have an example, and let's have an example a little bit deviating from the real floating point number. Let's assume to be in a decimal system because it makes things much easier to understand and the nature of the things is not altered. It's completely the same. Let's assume that this is the way the number is stored as a decimal number. In reality, it's a dual number, but it's something between 1 and 9 point, and then 4 digits after the decimal point, and then times 10 to the power of something. Okay, and I have chosen this number. It's an arbitrary number, and let's choose another one. And if we add these two numbers, then we see, okay, in both summands have 10 to the power of 8. So we know the result is 10 to the power of 8. And then we can add these numbers by 7, hold nothing, 7, 7, 7.4. So it's clear this is no problem. And this is really the way a computer adds. He adds in a dual system, but from the concept, it's completely this concept. So second example. In our example, we said this is a number between 1 and 9. This is a number between 1 and 9 times 10 to the something. And also in this case, it's 10 to the 8 both times. So immediately we can see, okay, let's add these two numbers. But now the result is not of the kind we store the numbers, so we have to do a shift. 12 and 10 to the 8 is to be shifted to 10 to the 9. And then due to that 7, this 7 is rounded to a 8. And that's the way it's implemented in your computer. It's a dual system, but the system is completely the same. Okay, third example. What if they're not of the same kind? If the exponent is not the same, then we have to shift. Let's shift the 6 to the 8, and what do we get? And then we have this number. And now they are of the same kind, and we can add and get 7, 7. There was some rounding, but that's the way things are done. Fourth example. What do we have? Not of the same kind, so bring this one to that. And then we have, what do we have? We have to do a shift from 1 to 8. So it's a 7 shift, 1, 2, 3, 4, 5, but then this number is shifted out of completely to the right. And what do we have? It's 0.0000 times 10 to the 8. And there's nothing left of that number. And adding that, we get. And that means that this number, there's no effect. Having a number and adding something can give us a result which is identical to this number. A plus something is A, normally only if this something is 0, but in this case we get A plus something is A, although the something is non-zero. Okay, so let's go to subtraction. It's of the same kind, so we can subtract how we learned at primary school 1, 1, 1, 1, dot 3, and this is the result. Second example. They're of the same kind, and then we have to shift, and it's 1, 2, 3, 4 shifted by 4, so we get 10 to the power of 4 and 2.0000. So if these were the numbers we are dealing with, this result is completely exact. But if this was the rounded version of some number and this also, then this result might be incorrect, completely incorrect. So instead of 2.0 times 10 to the 4, the correct result would be 2.4 times 10 to the 4. So the relative error is very large, it's 20%. So we have a big problem, we have big trouble if we subtract two numbers which are very close together. Because in this situation, if the numbers involved are rounded versions of numbers, then subtracting these numbers close together will result in a very large error, in a very large relative error. So what if we perform this operation? We have a number, then we add a number, and then getting the result. After that, we subtract the same number. Being a human, we see, okay, the result will be that. But what happens if the computer is to be doing that thing? Okay, he will add by bringing that to the 10 to the 7. And let's write that down here. And then doing the subtraction, we get, and now we bring it to the standard form, which results in this result. And so the correct result would be 3.3333, but our result is 3.3. So the relative error is larger than it should be. But now you may ask that why should be somebody such an idiot doing these things? I tell you that if you implement the solution of a system of linear equations, you do not exactly that thing, but very close to that thing. If you don't take care, it might happen that you add large numbers and later you will subtract large numbers. And that is to be avoided, because otherwise we have big trouble coming from the rounding errors. So let's make this example more extreme. And this time doing that step results in what? It results in a shift by 5, 1, 2, 3, 4, 5, and nothing is left. 0, identical 0, although the result is 33,333. So compare if you have a bank account and there are 33,000 euro, then somebody pays 4 billion, or in German 4 Milliarden, and then later taking off that sum. Then if this results in your bank account being on 0, that would be a horror thing for you, I think, because you lost 33,000 euro. Okay, let's have a more realistic example, 1/7 minus. So this is times 1000, this is times more or less also 1000. So we subtract two numbers which are very, very close together. What will happen? First, let's transfer that number into that system. Doing that, we get 1.4286 times 10 to the power of minus 1, which means 1/7 is 0.14286 and something. And then let's transfer that. And doing that, we will get 51000. And that is 1.5 times 10 to the minus 4. the correct answer, if you do that calculation with electronic help, you will get. And so we have a big relative error, and it's not so nice what happened. And let's have a fourth example. If you take the number 1 and then add on a real computer 10 to the minus 17, and you're doing that a lot of times, then correct result is, mathematically correct result is 2, obviously, but numerically the result will be 1. So the result will be 1, because if you add that number and that number, this results in rounding that to nothing. So result is 1, and doing that again and again, it stays 1. So it stays forever 1. In the end, the answer is 1. That is a very, very bad thing. I meant 10 to the 17. Okay, so we have seen 4 examples, and now we have a feeling that the way a computer adds and subtracts might result in problems. Now let's discuss multiplication and division, and the surprising thing is that compared to addition and subtraction, multiplication and division is very harmless. Nothing goes wrong, whatever the numbers might be. And we can add here the exponents, so we get 10 to the 11, and now we can do that multiplication. And how can that be done? How you learned at primary school. So 2 times that, and then 2 times that, and shift it 1 to the right. Then coming from that, shift it once more to the right, and so on. And we get a 2, a 4, a 6, a 8, a 10, hold 1, and now we take the rounded version, and this is the result. The last digit is not completely correct, but it's impossible to expect more accuracy. That the last digit might be incorrect, that's no problem. So this example was quite extreme, but no problems at all. And that's the true story. No problems with multiplication. What about division? Let's use that example and divide this number. So what do? Let's subtract the exponents and let's do that division how we learned at primary school. How is that done? So let's see, how often can we take that into that? 1 times. Then subtract 9, hold 1, 6. Then take a 0 from above. How many times can you take that into that? 1 times. And again 1. And now it's clear that it continues that way, because here we have the same number. So the result is 1.1111 times 10 to the 8. And that's the correct result. So absolutely no problem with multiplication or division. So let's switch to MATLAB, to Octave, and there I will show you real examples. Okay, so let's do these examples. What if we subtract 1 divided by 3 minus 1 divided by 7? It's 0.19048. What is the result working with fractions? 4 over 21. But what if we do the following? Let's take a large number. This is some example for large number, very large number. And now let's add this large number to 1 divided by 3. Then there will be a rounding error. Then a lot of information of 1 divided by 3 is vanishing. Minus, so doing this operation, also a lot of information of 1 divided by 7 will vanish due to the addition of a large number. And now if we subtract, we should get the same result as above. But let's see what happens. You say nothing happened, everything is correct, but let's change to that. And now the result is that. Okay, and now we see the following. Comparing these two numbers, this digit is correct, incorrect, yeah? From 9 on, things are incorrect. So all these digits vanished, and this is not really a surprise, but it's very convincing, I think, seeing the real MATLAB, the real Octave, which is a professional tool, that there are these problems occurring. I was only able to believe because I tried it by myself, so it's very surprising. And what if we take a much larger number? Let's make this number much larger. This is a very large number, and now we see the result is a 0, although the correct result is 0.19. And this is very bad thing. This is a real MATLAB, real Octave, real professional programming, and the result is 0. So this really happens. Let's take a second example. Let's use again a large number, but not really so large, 100,000. Let's use 100,000 numbers. A is an array of 100,000 numbers. B is also an array of 100,000 numbers, and we can sum the entries of A, and we can sum the entries of B, and then we can subtract these two numbers. And then we can subtract these two numbers, and in this case the result is minus 48. Okay, and now let's do the following. Let's add to every entry of A the large number, but not really so large number, 100,000. This number, this is a syntax which is mathematically nonsense, an array plus a number, but MATLAB and Octave is interpreting and says, okay, you want to add the number to every entry, okay, plus n again, and now we should get the same result, minus 48. But what is the result? It's minus 48, but from that digit on, things go wrong. And hui. And what about if we take a little larger number? Then we have this digit wrong, and this is really a bad thing. So now we have a good feeling what can go wrong, and we see that addition and subtraction is a real problem, and we have to be aware of these effects or later avoiding these effects. But maybe you think, oh, I don't think that this is really interesting. It's an academic example I will never encounter in reality, things like that. But this assumption is wrong, as we will see.